Yeah, so to answer Lucas' question again, basically we voted inside the program to change the program's name to the correct thing that we are doing, which is computer engineering. I don't know why this hasn't been done earlier, because software system engineering means nothing in the world of computer science and computer engineering. It has no meaning. I believe it might have been something that Arkin was doing when the program name might be in Germany, and somehow people just directly translate to English without consulting what is the proper English name of something that we are doing right now. And in science or engineering, there's only kind of three school of thoughts, right? Not school of thought, but like three big school that involve things that are related to computer science, computer engineering, and electrical engineering. Even communication engineering is a bullshit program that I think I'm recording, am I? Okay, sorry for using that word, but it is a communication engineering is something in the middle of like computer engineering and electrical engineering. So people who do electrical engineering are supposed to know things that are involved in communication, like signal processing. And to have such a separate topics for each of the program, I feel that's bad because it doesn't cover enough of the breadth, right? I don't want my student who are working in computer software to not know anything about the hardware. That's dumb, to be honest. Like, it's a bad way to design a program. So we talked and we actually ended up kind of like modifying the curriculum to some extent, but it's not hasn't officially been changed yet. But the fact that you are required to learn computer architecture is one of the changes that we apply to the SSC program, which is now changed to computer engineering. We want you guys to know the basics of the basic of how computer works and the basic of how software is being developed. And to be honest, I'm still not happy with having the software engineering class being the required class because software engineering is not the same as computer engineering. Software engineering has a lot more to do with management and the soft skills that to me are not that important. There are more important topics that you're supposed to learn for something that are in the engineering program. And while I'm not saying that software engineering is not useful, period, it's a lot less important than other things that could have been a required topics uh, like system topics, or like if you want to do image processing, things like signal and system, the maths behind convolution, fast Fourier transform, how do you actually do a transform really quickly, what does it mean to, I guess, switch things from time domain to frequency domain and such, right? Those are always helpful. And I took those class and I actually benefit a lot from it. I know how, I know roughly in a high level how image processing work. I know roughly how convolutional neural network works and things like that from learning this like fundamental classes. Anyway, so hopefully that kind of address the name change. So yeah, we will, I think in the next iteration of the ESSE curriculum, we will rename officially to computer engineering. Right now, we are changing the website to computer engineering so that we no longer use term software system engineering, which to me means nothing. Yeah. And today we will talk about something that's super popular nowadays in AI, machine learning, data analytics, and games. We've been using these things for playing games for a long time. which are the GPU, video cards, graphic processing units, they are all the same thing, right? So hopefully your machine comes with the GPU. If you don't buy a separate GPU card, say you have a laptop, they actually come with an integrated GPU. They help rendering video, they help rendering some of the games that are more lightweight that you play. If you want to play crazy, really high-end games, then you need to buy these GPU cards, right? So on the picture here, I show the actual cards that from NVIDIA RTX 2080 Ti, which is really high-end for a GPU that you can buy these days. Definitely better than the GPU I have on my machine right now. These cards would be able to render the graphic behind all the 3 games that I show you over here, which I all play. So these are awesome games, and if you haven't tried, if you like gaming, you definitely should try those. But that aside, the graphic processing unit is responsible for drawing whatever you saw in the game, right? All the animation, all the 3D texture, including things like smoothing, lightening. Most of these are done by the GPU. Today, we'll go into the detail on why does it make sense and why what's the reason why the GPU is the only right now processing unit that kind of like maps really well this application, and you cannot really do this on the CPU. So how many of you actually tried running these games on a CPU or on a laptop? Without the GPU or without the dedicated GPU. One thing that you might have realized is you need to change the configuration to like low setting, where everything will look pixelated, and you might actually play and might throw up because it will not be able to catch up to the monitor frame per second. Anyone want to take a guess on like what's the usual frame per second that your monitor should be able to render? These I have seen 4 different numbers for different brand and how high-end the monitor is. So there are 60 hertz, which is like a default monitor that I believe that most of you have right now, including myself. There are 72 hertz, which is a little bit better. And then there is the monitor that can do double the rate, which is 120 and 144 hertz. Those number means that within every second, I need to be able to draw 60 different things. Each of these frame has to be drawn in a strict interval, 160 of the second, 172 of the second, 1 over 120 of the second, 1 over 144 of the second. Anyone want to take a guess? What will happen if I fail to draw an image during this strict interval? What might happen to your eyes, actually? Essentially, you think about it this way, what your eyes will see if your GPU is not good enough, right? So it failed to draw some of those images and you ended up with things like 30 frames per second or 25 frames per second. What happened is your eye would process those images, but at a different rate given the same period of time, which means that your brain has to work harder to kind of like trying to understand what you see. And if you are older like me, who are 30 years, how old I am, 30 years old, what happened is when you play these games in the low frame per second, I feel like I want to throw up because my brain cannot keep, it's like me being on a roller coaster, which I'm okay when I'm young, right? Right now, I'm not that okay. And that's a fact that you will learn in a few years. So any questions about how GPU is being used to play games? Hopefully it is none right now. Then, aside from playing games, right, let's come to a more like academic side of things. There are multiple things that GPU can do What happened is around year, I think 2010, researchers realized, I guess the people who do machine learning and people who come up with graphic cards are talking, and they're like, wait, a lot of these workload, visual processing, domain-specific language, DNN, deep learning, convolutional neural networks, fast Fourier transform, linear algebra, math algorithm are really GPU friendly. Why is that the case? A lot of them involve things like matrix multiply, a lot of them involve things like convolution, a lot of those involve things like and Fourier transform, which is another fundamental math operation. All these things are really, really friendly toward how the GPU is designed. So by year 2010, you see a lot of research going into, okay, given this application, how can I run this on GPU and how much additional performance do I gain? These applications range from machine learning, AI, bioinformatics, like weather prediction. You can look into SLAM, for example, is being done on a GPU as well, visual processing, image segmentation. All those tasks are now being shifted toward the GPU. And these days, it's actually now shifting toward the specially designed accelerators, which is a special type of hardware that's capable of running these things. And now that we talk about running a server-like workload, like workloads that people typically would run in the cloud, one thing that GPU is doing is, well, why can't we have GPU in the cloud, right? So NVIDIA came up with the design that allows the GPU to be run in the data center back in the need to time share. These days you can kind of partially, spatially share through virtual memory. And with this, GPU now gains the popularity through their massive parallelism, right? So hopefully by this point, you kind of buy the idea of, okay, GPU is getting really important beyond gaming. And GPU essentially is using kind of like three concepts: Simdi, fine-grained multi-threading, and predicated execution. Anything that looks friendly to you, these two things, right? We covered this a few times in the class. So before we begin, actually, no, we will not discuss parallelism because we already discussed it, my bad. So we'll go through with fine-grained multi-threading. Sorry about that bullet point. I forgot to delete it. This was intended for the undergraduate level class, so I need to discuss parallelism first and what is parallelism. Right now, let's actually review fine-grained multi-threading. Traditional multi-threading is basically when you have each thread running on the CPU, right? If there are multiple threads or multiple tasks that you want to schedule, what will happen is each of these threads would take turn running on the processor. Let's say you have a multi-core CPU with 4 cores. Each of the threads would basically take its own time running on one of those 4 CPU cores. Then the OS and the hardware will work together and come up with a policy saying, hey, that thread has been running on processor 0 for a long time. Let's switch it out, allowing the other thread to come in and run on CPU 0 or processor 0. These policy heavily determine performance, right? So if you're curious about this, we'll talk more about how the hardware manage this. So we'll talk about the hardware fraction of these multi-threading in the next lecture when we cover coherency and consistency. But right now, just understand that there's a policy coming from your operating system, Linux or Windows, and the hardware. They will work together to kind of like figure out who is running what at any given time. Then there's hardware multi-threading, where one CPU can run multiple hardware threads. And this is basically the concepts behind things like Intel hyper-threading, where you maintain multiple contexts within the hardware. The main difference between software and hardware multi-threading is software multi-threading will have the context saved in the memory by the OS. So when you switch between threads, you need to actually recover the context. Hardware multi-threading saying this, hey, I know there's pipeline register, there's program counter and register files. I'm gonna make a copy for each thread. So there'll be 2 copies of the program counter. There will be multiple copies of the register files. Each one of these will be responsible for certain threads. For example, in an ARM architecture, right? If you take the embedded system class, you notice that, hey, the register files contains multiple registers, but some of them are special toward the kernel. Some of them will be special toward the user. Those are specially designed so that you can do hardware multi-threading. When the kernel has to actually switch in, they will actually have its own copy of the register file ready to be run. Each of these threads runs different processes, which means that, one thing I need to tell you is the difference between the process and the program. A program is one single thing, and when you run a program, you can run it multiple times, right? You can have multiple Chrome windows, you can have multiple instances of YouTube, you can have multiple word processing that is running. Each one of them would be like managing one of your Word documents. These are a program that are run on multiple processes. Is an instance of the program that's being run right now. The benefit of hardware multi-threading is basically you only have one CPU to run things. So if you have hardware multi-threading, you can switch between thread 1 and thread 2 whenever the pipeline is trying to insert bubbles. So instead of inserting bubbles, because I'm stalling, I'll just put in the added threads instruction into my pipeline. And that's the concept behind simultaneous multi-threading. And you might have realized I'm going a little bit fast here because we cover all these things from before the midterm. Simultaneous multi-threading is kind of like this. Let's say the processor is waiting for the main memory, which takes some time, right? 12 to 50 nanoseconds. If you have queuing, that can be 100 nanoseconds or 100 cycles. Actually 200 cycles or 300 cycles, depending on how fast your clock is. So with that in mind, what you will run into is would be some instance of time you're waiting for the main memory, you're waiting for the L2 cache. The idea is, okay, while I'm waiting, I'm switching to another thread to keep my pipeline full. Basically, the CPU will be doing something useful, right? And it allows concurrent execution of useful works. Intel hyper-threading is actually one of the examples of these particular technology. The trade-off is you need to figure out, okay, what's my policy? When should I switch? On L1 miss, which is around 4 cycles, or do I switch between each L2 misses, which would take around 11 cycles, 10 cycles, depending on the technology. This means that there's a cost and performance because every time you switch, there's a chance that the switching thread never gives back the CPU because it's a lot of compute instruction I never stop, right? So what's the policy there as well? If I have thread 1 running for 500 cycles now, will I ever issue thread 2's instruction? Right? If I'm not stalling, why do I yield? Right? So this is a policy in the hardware you need to basically figure out. Another end of the spectrum is this. Let's say you have a pipeline stall in whatever way. We don't do data forwarding. We don't do branch prediction. We will just perform fine-grained multi-threading. You add so many threads in the hardware so that every time you can switch into something new inside the pipeline, right? So that this number, note that this number can still lead to stall because of limited bandwidth, right? So this is how fine-grained multi-threading can work. So let's say, let me use the pen. So let's say I have a pipeline, fetch, decode, execute, memory, and write back, right? And let's assume everything takes 1 cycle. For now, I know this is not true, but let's assume that. In this case, how many threads do I need to actually enable fine-grained multi-threading? Assuming everything here takes 1 cycle.
5.
Yes, 5 threads, right? So let's say we have thread 1. I'm going to use a different color for each thread. Thread 2. Thread 3. Okay, that's a bad color. It's so hard to see. Thread 4. And thread 5. I'm kind of like changing the color into more like a reddish tone from blue. Okay, so in the first cycle, thread 1 come in, right? That's it. I put in thread 1, instruction 1. Thread 1, instruction 1, I would be instruction number of that thread. In the next cycle, what happened? Thread 1 moved to decode. Thread 1, instruction 1. Thread 2, which is in green, would come in. Thread 2, instruction 1, right? And that's it for the first cycle. For the second cycle. What will happen in the third cycle is, well, thread 1 proceed to the pipeline. Right? Thread 1, instruction 1. Thread 2 will be, okay, I'm done with fetch. I'm going to go what? Thread 2, instruction 1. And then yellow. Thread 3 come in. Thread 3, instruction 1, right? That's the third cycle. Then in the fourth cycle, thread 1 come in from execute going to memory. Thread 1, instruction 1. The green thread here, move in here. Thread 3, instruction 1. And then the yellow thread comes in from fetch going to decode. Thread 3, instruction 1. The orange thread comes in. Thread 4, instruction 1. Right? And then in the fifth cycle, thread 1, instruction 1 comes into the write back. In green, thread 2, instruction 1 go to the memory. Thread 3, instruction 1 go to execute. Oops, I'm supposed to use orange. No, give me orange. Thread 4, instruction 1, and then now that we have the fifth cycle, thread 5, instruction 1 comes in here. What happened in the sixth cycle is thread 1, instruction was done. Yay. Thread 2, instruction 1 is in write back. Thread 3, instruction 1 is in memory. Thread 4, instruction 1 is now in execute. Thread 5, instruction 1 is in decode. So what do I put in the fetch? What do I put in the fetch unit here? In the fetch state? Well, back to thread 1, right? Instruction 2. So with this, what is the throughput of thread 1? How many cycles do I need to finish one instruction for thread 1?
5, 6.
5, right? I take 5 cycle. Fetch, decode, execute, memory, write back. After 5 cycles, you're done. So each thread's throughput is 0.2. 0.2 instruction per cycle. 1/5. The processor throughput when collectively looking out of 5 threads is 1. Every single cycle, I'm doing some useful work and I can retire one instruction. It just happened to be one instruction from all the 5 threads, right? So the downside of these, which is also applied to the GPU, you will have a really horrible single thread performance. Really horrible. Because you do fine-grained multi-threading, each thread would be really slow. But the processor will always do some useful work. So collectively as a unit, the performance is really good because you never have to stall, right? The other downside is, well, now you have to maintain 5 threads, right? So you need extra logic to keep the threads context. Things like program counter, register files dedicated for each thread. They have to have their own register files, right? Because each thread has its own internal data. So the third thing is your program has to be really, really friendly towards this model. It means that you need to be able to spawn multiple threads in your program. So let me ask you a question. Let's say I have a program that's only can spawn 2 threads max, right? I can only spawn 2 threads max for some reason. The algorithm works that way. It's so sequential. Will I ever get a benefit running things in this fine-grained multi-threading with the 5-stage pipeline? Or should I just do data forwarding and branch prediction?
There's maybe some dependencies or
Yeah, so data forwarding would help with dependency, right? So what you might want to do in the hardware is like if you can only spawn 2 threads, let's just use the typical processor, do data forwarding, do out of order scheduling, and do branch prediction. That would definitely be faster. I can guarantee with 99% confidence that they are going to be faster than running those on a fine-grained multi-threading processor, right? So the next thing that the GPU uses is predicated execution. Recap. If you have branch like this, typically you do branch prediction, right? But other method, one of them is called predicated execution. Convert control dependence to data dependence. What do they mean? My instruction might or might not happen depending on the previous instruction. Things like compare. If compare is resulting in 0, or less than, which is negative value, sorry. Then you do this add and subtract, otherwise don't do anything. So this is called predicated execution. This is used in GPU when they need to handle branches. So they don't do branch prediction, they would do predicated, like a form of predicated execution. Benefit is you get hard to predict branches and allow this compiler to kind of optimize your code, but this costs useless work and requires additional hardware and ISA support. The last thing that I need to cover before I talk about the GPU is called Simdi. Simdi is similar, not similar, but has the same thought process behind vector processor and VLIW, very large instruction windows. If you're curious about these in detail, because of the interest of time, I would have to cover that in the advanced architecture class. But the concept of SIMD is something like this. If you want to run 64 different multiply on 64 pieces of data, you know that it's the same thing. Multiply, 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 right? So the instruction will be the same instruction, multiply. In a typical processor, it means that you need to fetch 64 times, decode 64 times, execute 64 times, memory and write back. Everything will be done 64 times. SIMD processor look at this observation, and because they are the same instruction, do you need to fetch 64 instruction, decode 64 different instruction? No, because they are the same instruction. They are multiply. You just need to apply the actual multiply on 64 different pieces of data, right? That's why it's called SIMD. SIMD stands for single instruction, multiple data, means that you have the multiply instruction that is multiplying 64 different pieces of data together. The CPU has this support, the GPU also has this support. The CPU support is a little bit less wide. The GPU support is about 32 to 64 elements wide. So you can do 64 multiply, 64 add all together in one single instruction. And the requirement here, so the big thing here is you have one fetch, one decode, a bunch of execute units, right? Then you need to make sure the program counter points to the same instruction on all the 64 operations. It has to be a multiply. The same thing. It has to be its add. It has to be the same exact operation. And the GPU is essentially a combination of these things that we described, right? It's a Simdi plus fine-grained multi-threading. So if you have a GPU program, the GPU is being organized something like this. You start with a program written in CUDA or OpenCL. If you use TensorFlow or if you use PyTorch, eventually these are what you get. CUDA or OpenCL program, those API will eventually call libraries that will be written in these languages, CUDA or OpenCL. So let's say you have the program in this kind of language, you compile it. When you compile it, one other thing that you need to specify in the CUDA or OpenCL program is how many threads do you want for this program, for this function, for this lines, for this for loop? You specify number of threads that will be grouped in this unit called a thread block. Sometimes this is called a grid. They are the same thing. It's a collection of different threads that the program can spawn. The program can spawn thousands of threads, tens of thousands of threads. Each of the thread block will be then subdivided into a smaller unit called a warp. A warp is, right now, let's just look at this one row of threads, right? A warp is just that one row of threads. Typically, the warp size is equal to how many ALUs do you have in each GPU core. There will be multiple thread blocks from your program, and there are multiple GPU core. NVIDIA called it Simultaneous Multiprocessor, or SM. Sometimes they call it shader core, same thing. It's the actual GPU core that consists of fetch, decode, and a lot of execution units. So you have one fetch, one decode, tons of execution units. The thread block will be forwarded to the core, basically similar to how the CPU takes in all the instruction inside the CPU's memory. These thread blocks, the instruction will get copied to GPU memory. The core takes the instruction and say, okay, I'm running these things. When you run this, a warp, that one row, will all get forward to the execution units, as I show here. All together, all the 8 threads from this example will be executed together because you have one fetch, one decode. So this is one fetch, one decode, 8 different ALUs operating on 8 different pieces of data that are running the exact same instruction. Again, they have to be the exact same instruction. This thread block will be forwarded to our GPU core, right? And then the GPU core will take this thread block and run it. One thing when you read the CPU spec sheet, especially the one coming from NVIDIA, you might see something that this terminology, CUDA core. CUDA core is actually just one execution unit. It's just this small thing. They are not the actual core. They are not the actual core. This is what happens when you have a business folks trying to PR for the products, right? Sometimes they are misleading. This is actually one of the misinformation stunt from NVIDIA, which they do quite a lot these days. If you understand how GPU work, you then realize that a lot of things here is not as really awesome as what they claim. They are really good at running certain things. Really good at running certain things, but they're not like a silver bullet for every single program that you need to run. So don't ever fall into that thought. But they're really good at running programs that can spawn multiple threads. Each thread run the exact same thing. Otherwise, the GPU suck. Otherwise, the GPU will actually be really bad to run program that is single-threaded or only spawn a few threads where each of the threads are doing totally different things. GPU will not be able to run that really well at all. CUDA core is one ALU. Inside the GPU core, the actual processing core, they will consist of 32 or 64 CUDA core because they have 32 to 64 ALUs. And then you have 15, 30 different shader core, simultaneous multiprocessors, or the actual core. Any questions so far before we go to our friend's 5-stage pipeline? Any curiosity questions or anything you want to ask? All right. So if you have questions, feel free to ask them at any point in time. You can feel free to raise your hand. Feel free to just unmute your microphone and ask the questions. So let's go back to our friend, the 5-stage pipeline, right? You fetch, decode, execute, memory, and write back. If you are on the CPU, let me do everything in a really high level, right? On the processing side, you have instruction cache, you have the decoder, you have the ALUs, load store unit, which handle memory requests, write back. Any questions so far? This is like a really, really simple 5-stage pipeline in order. Then, if you want to make it fast, you have branch predictor. You have a lot of logic to support out-of-order execution, which also include the future files. To make the memory fast, you add the SRAM cache. Right? Then you have the actual architectural register files, which is actually updated by, not updated by, but updated at write back, so the programmer can see that. So if you look at this, if you look at these diagrams, many of these things are being added to improve single thread performance. Whatever program you're running, they are supposed to be fast. So you have the branch predictor, you have the out-of-order scaling logic, you have the SRAM cache, so that everything will rarely stall the pipeline. Any questions so far about the CPU?
Not directly to the CPU, but once I saw this, what about caching for GPU? Is that possible because of the high amount of data?
That's a great question. So GPU do have its own cache. So what are the trade-offs the GPU do? So actually that's kind of fall directly into the next slide. So if you look at the GPU, what happened? I'm gonna take the branch predictor out. I don't care to take too much space on my processing die. I'm gonna take everything that related to the out-of-order scaling out. I'm making room for something else. As I said, there's a bunch of ALU, so I'm gonna add tons of adder and multiplier. Then for the SRAM, well, not yet. Then to maintain all the context of fine-grained multi-threading, you are going to have large register files, right? Because you have so many threads, you need so many register files for each thread. Then the SRAM cache, they don't totally eliminate that because you need the cache, they are useful. But they're a lot smaller. And then the special thing is there's a two part of the cache. One of them is software managed. When you write the program, you can manually manage the cache. You can actually define how much of the software managed cache that you want. And then you can say, okay, bring this address to the cache, use it, then kick it out from the cache. Then there's a typical hardware managed cache. Are they going to be smaller? Yes, these are a lot smaller. Considering you're running thousands of threads at the same time, your cache is still kilobytes of data. So when you divide kilobytes, like say 256 kilobytes of data per thread, you get about 256 bytes of data, right? So these are to cache like a really, really heavily used cache block. If it's not heavily used, they'll all go to the main memory. So I hope that answers your question a little bit out of the cache, right? We do have the cache in a GPU, but it's a lot smaller, especially when you compare per threads, right? Number of cache per threads, it's way smaller. So many things of these addition done to improve the instruction throughput. What is instruction throughput? How many operations I can do in one cycle? Because I add so many ALUs, if I make this assumption that my program is Simdi. This is a big assumption, but you need to write the program this way. if my program is written in a Simdi manner, this will be really fast. Right? This will be really fast because I would just have Simdi. Each cycle, I will run 64 add, 64 multiply. Each time, each cycle, as I go through the pipeline, I do fine-grained multi-threading. I then switch from the first 64 threads to the next 64 threads to the next 64 threads. So if I make a really too big assumption, program is SIMD-like, you can have the same instruction doing the same thing over and over. Your program can spawn so many threads. If my program behave in this two manner, it would be fast on the GPU, but not all program behave that way. Right? A lot of the program or a lot of some of the function inside the program behave that way. But if you have a lot of things like shared structure, like a shared linked list, no, don't run it on the GPU unless you know what you're doing. Otherwise, it's going to be slow. So execute a compute instruction on a CPU is one instruction at a time, one warp at a time. And inside the warp, there's so many operations, but they have to be the same exact operation. It'd be 64 multiply, 64 add. The benefit is you have really high throughput. And then when you have instruction that take more than one cycle, you will do something like this. So you have a GPU core. As I mentioned, inside the third blocks, there are multiple warps, right? In the actual GPU core, you actually schedule multiple thread blocks. So you ended up with 30, 40, 60 different number of warps inside the GPU. These warp, let's mark them A, B, C, and D, and blah, 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 etc. until like warp C, A1, A2, A3, blah, blah, blah. Basically, there'll be so many warps in there. Each of these blocks is a thread. The way it runs over time, if you look at the time on this top to bottom axis, the GPU core status will be remain active by taking one warp, sending to the ALU in a lockstep manner. Lockstep manner means that everything here in the warp will be done together. Then the next cycle, fine-grained multi-threading kicks in, switch to warp C. Warp D is now in the second stage of my pipeline. Warp C comes into the first stage of my pipeline. I move one cycle. Warp D is now in the third stage of the pipeline. Warp C is the second stage of the pipeline. Warp B is now in the first stage of the pipeline. And then they will rotate, basically. Unless a warp A is a load and store instruction. So if you look at this diagram, how many loads do I issue at once? There are 8 threads on 8 different pieces of data, right? So I'm going to issue 8 loads. So if warp A is a memory instruction, I'm going to issue 8 loads. And this will take a while because I'm going to actually demand a lot of data. So warp A is stalling. Warp B, C, and D would be running things, putting things in the pipeline. GPU core will become active. Something is always going into the pipeline. Something is always going out of the pipeline through write back, right? So each cycle, if you have 8 threads in a warp, each cycle, this GPU core would issue and finish 8 instructions. So the throughput right now is 8 instructions per cycle. But let's say all these warp is now running into the memory instruction, which is actually typical because the way you write GPU program, if you need to load the data, all the warps will reach that point in a similar fashion. So there'll be some point where all the warps say, hey, I need the data. At this point, you issue 32 loads. This is going to contend in the hierarchy, right? You're gonna issue so many loads. It will be queued up in the memory scheduler, and it will take some time to finish all the 32 loads. So the GPU stall until one of the warp got the data back. Then GPU can resume the execution. Right. So this is how GPU run. Any questions so far? All right. So we are breaking that black magic box that NVIDIA is giving us. So hopefully by this point, you start to understand what is beneficial with the GPU, what are they really good at, and what are they really bad at. So let's discuss some trade-off. If you give you a really high throughput, the reason why is that the maximum instruction per cycle is essentially number of cores multiplied by number of lanes. Number of lanes are the number of ALUs that you can feed into the execution units. So these days you're looking at thousands of instructions per cycle, way more than the CPU, if you can somehow get to that maximum number. Horrible single thread performance because there's nothing to improve single performance of one single thread. Basically, there's no complex out of order scheduling. There's no branch predictor. You can't even feed in the same instruction when the same threads are already have instruction in the pipeline. So the program performance depends on the application's parallelism. If you write a really good parallel program where many of these operations are the exact same operations, they're going to be really, really fast. What is a common operation in machine, like deep learning? Multiply and add. Right? They do a lot of multiply, a lot of add, a lot of data load, a lot of data store. All those are just a few instructions that they have to do together. So deep learning is really, really friendly toward GPU. The code, if they have a lot of critical sections, these are going to be really painfully slow. So one thing you can do is, let's say your program. So let's say if you look at this program, right? This is a serial portion. And then you have this parallel portion. This is actually requiring a lot of work. These days, if you have a program like this, Amdahl's law, right? Serial portion would dominate the performance. So one thing you can do, shift it to the GPU because I have so many cores. I'm going to run the parallel portion on a GPU. Then for the serial portion, I'm going to keep this on the CPU because CPU is good at running single thread things, right? So in a typical program, if you say you want to take advantage of the GPU, you need to really know what your program is, how that's organized, and how to actually, which function would be beneficial shifting to the GPU. The way you write the GPU program is kind of similar to C, where a fraction of the code on the program would be, okay, these are done in the C code. You don't need to run this on a GPU, and then you declare some big function that would be running on a GPU, and then the GPU would take it, run that function, return the result back to the CPU, and you are faster. Basically, your program are faster, and you're happy, right? So what are the use case of the GPU? The obvious use case that we've been using this for 20 years, so quite a long time. Graphic application, because the graphic pipeline has a lot of redundant instructions. Why? You are going to draw a lot of dots. You are going to connect those dots into a lines. Then with the lines, you're going to draw triangles, right? The triangle, then you you convert that from vector to pixel bitmap. Same operation. Then you smooth out the surface. So the smoothing is also the same operation on multiple objects in your image, right? Then you draw the surface, map the texture, right? Same operation again. Hey, I have this object, I have this file, which is a texture that's supposed to go in on top of the object. So I'm gonna map that. Compute lighting on each of the pixel, how bright each of the pixels should be. Draw out, figure out which object is in the front from the camera point of view. What should I see? What should I draw on each of the pixel, right? Rinse and repeat. So all of these are a lot of adding, a lot of multiply. a lot of independent data that are run in parallel, right? So they are really fast to run on a GPU. Any questions so far? All right, so if there's no question so far, let's take a quick break. We'll meet again at around 10-ish, 10:03. Let's do a 10-minute break, 10:03, 10:05. And we'll continue and talk about what if you have branches, because I told you earlier, GPU mainly consists of like 3 things that we learned: fine-grained multi-threading, Simdi, we cover that, and that's exactly how GPU core run. Predicated execution is how GPU handle branches. So we'll resume with the discussion on how console flow instruction works on the GPU. We'll be meeting back at 10:05. All right. So let's take a quick break, go get coffee. We'll personally go get coffee as well. And we'll be back here. Hopefully I'm not too caffeinated after the coffee, because I feel like today I'm talking pretty fast for some reason. Okay, so quick break. We'll meet at 10:05.
All right. Are you all back?
Okay, it's 10:05, so let's resume the lecture. So when you run into control flow instruction, which is things like if else, for loop, over here is one example of the if else control flow instruction. Inside the warp, as I said, there are multiple threads, right? So if I have a conditional expression like this, if A is 0, do something, otherwise do something else. One thing that can happen is within the warp, some of the threads will be true and some of them will be false. So let me represent this in a different color. True is a blue box, false is a red box. What you need to do is, well, this is predicate execution. I'm gonna go through my code from top to bottom, right? What will happen with the top part? Only 3 of them would be enabled. There'll be a mask that say, hey, don't run whatever code is in here. Because the conditional code tells me I'm not supposed to run this. So during the do something phase, the first thread, the second thread, and the fifth thread are the only 3 threads that is active and running something. Then the other 5 threads will be running something on the else part, while the true threads would be not doing anything, right? So over here, one thing that you will notice is that the utilization of my ALUs inside the GPU core is not fully 100%, right? In each of these instructions, there were times that only 3 out of 8 run. The other time, only 5 out of 8 are being run, right? So this problem reduces GPU utilization. So typically, if you have a lot of if-else statement in your code, again, this can reduce the performance of a GPU program. This problem is called branch divergence, right? From the earlier example, you do not actually utilize all the execution units at once. And again, this is called branch divergence, and this lower GPU performance. So let's go through some example, right? Let's say I have a code right here, and assume each GPU core has 64 lanes, and load and store magically, they are free, right? What's my core? What's my GPU core's utilization? And let's make a few assumptions. This is instruction 1. This is instruction 2, which is an add. We'll assume there's no load and store instruction. Somehow your data is already there. This is instruction 3. And this is instruction 4. If I have a code like this, I'm going to give maybe 5 minutes for this entire question. The first question I'm going to ask is for the first warp. If I have 64 lanes, right? I look at this. The first warp would consist of A of 0 to A of 63. So can someone tell me, out of the 64 lanes that I'm dealing with right now, A of 0 to A of 63, and let's make the second assumption. Second assumption is A of n is equal n. So that's our second assumption, A of n equals n. If we make these assumptions, how many of the first warp go into the if and how many go into the else? So that's my first question. If I assume A of n is n, how many of the first warp go into the if? How many of them go to the else? All right. So how many go into the if? Which of these are divisible by 3? 22 going in here and 42 going in here. Why? 0 to 62, right? 0 to 62. Or I mean, you can just divide by actually from 1 to 63. There are 21 of them that goes into the if, right? And then A0 was also divisible by 3. So that's 22 elements going into the if and 42 going to the else. If I go into the if, how many instructions am I processing? I'm going to process this instruction, instruction 1, instruction 2, right? So if I'm running the else, and then I don't run this, I don't run this, right? So if I go into the else, I'm going to use a different color, red. I run the comparison. I don't run this instruction. I run these 2 instructions, right? So out of the total 4 instruction, which can translate to 64 plus 4, this is my maximum throughput, right? Because each lane, there are 64 lanes, each lane supposed to run all the 4 instructions. That's full utilization. This is 64 multiplied by 4. 22 of them run only 2 instructions, and the other 42 of them run 3 instructions, right? 1, 2, and 3. And 22 of them run only 2 instructions, 1 and 2. So this is my GPU utilization. Any questions so far? Basically, if you do this math, it answer for the first 64 elements. This is my utilization.
So in this configuration, this means one block they have 64 threads.
Yes, 64 threads. Okay. And in the if else, for the if part, only 22 threads are running. In the else part, only 42 threads are running. The other 22 are not running. Right. So these are things that reduce GPU performance, and they are pretty significant. If you look at this, it's actually pretty significant because what if the if part is not 1 line long, unless it is 1,000 lines long? It means that those 22 threads will be running for 1,000 lines, right? And then the other 42 would only run for 2 lines. Most of the time, GPU in this case, right, if it's 1,000 lines long, will be running only about a third of what they can do, right? Roughly a third of what they can do, which is pretty bad. Somehow you get like 60% slowdown, right? 60% less throughput. So that's the problem with branch divergence. The next problem I'm going to talk about is about the data access, right? Similar to the CPU, the GPU also have the load store unit and a typical like hardware managed cache and all the structure that actually allows you to access data in the hierarchy, right? The big problem with the GPU, as I showed earlier, is, well, first of all, most GPU doesn't really support the similar version of the virtual memory as we know it from the CPU. They have some form of virtual memory, but the GPU driver will be the one handling the memory location with the GPU hardware. There's no OS on a GPU. There's no operating system, so everything has to be done from the driver. And where's driver installed? On the CPU OS. The GPU driver is inside the GPU OS. GPU driver is inside the CPU OS, my bad, CPU OS. This fact doesn't mean that you not get the typical VM benefits, right? While some of these will not give you proper memory protection, they're still not giving you a large memory, like illusion that you have large memory that are like equally fast, but you still got like some illusion of like contiguous single address space memory. And they did a better job from Volta onward. So I talk about the two of the work I've done, right? Mask and Mosaic during the virtual memory lecture. So those two papers, when I presented at the conference, I was told by people from NVIDIA that, hey, this is roughly what they are trying and doing on their GPU, which is a good start, right? Which is a good start. They have some limited version of virtual memory support. If you actually run and try to do things like demand paging, you then realize that, hey, this thing can be pretty slow. And you need to kind of manage it well and manage it manually. The annoying part about this is you need to manage it manually. Unlike the CPU counterparts where you have the OS, the operating system would kind of like almost doing that for you. Okay, so these are some of the downsides. I'm going to expand some of the work I've done on the GPU today and talk about how to kind of address some of these concerns. So let's first recap on how the CPU access the cache. So let's say you have two loads. One of them is a cache hit, the other one is a cache miss, right? If you have these two loads, the one that has the cache hits will get the data first and resume the execution, right? You stop stalling the pipeline, you resume, and everything is happy. No, everyone is happy. Sorry about my grammar. Then the load A, which missed in the cache, they have to go to the main memory to get the data, right? And the stall time of load B is going to be less than stall time of load A, right? So one benefit that you can clearly see from this example is the cache. If the data is in the cache, the stall time reduces significantly. Memory access are much faster if you hit in the cache. Everyone with me so far, right? Benefit of the cache, you can reduce the access time to get your data in the CPU. Let's talk about the GPU. And let's say I have a warp that looks like this. The green box are threads that hit in the cache. The red boxes are threads that miss in the cache. And you look at the time. For those that are cache hit, they get the data quickly, right? So you get the data right away, or like in a few cycles. In the GPU, in reality, these are still quite a long time because of certain things that I will explain to you. But it's still not bad. The other 5 threads go to the main memory to get the data. Any funny thing that happened here? When let me ask you this question. When will warp A be able to resume execution? Can someone tell me when will warp A be able to resume execution?
Getting all data of each box.
Yes. So every single box here, the 8 boxes, are the 8 threads. You have to have all the data back, right? So the stall time of warp A is going to be that long. You see the problem here, right? I have a cache. The cache doesn't really provide the latency benefit unless everything hit in the cache. So that's one thing that you might want to do when you write a program in GPU. Try to write a program such that when you break it down into threads, they're kind of like being grouped together in the sense that if they have cache hits, just make sure they hit together. Otherwise, just make sure they're just missed together. That's fine. So now I'm going to start shifting into one of the work I presented in 2015, which involved that particular problem, where you have this problem called memory divergence. This is the exact same figure. You have a warp. They are not all of them hit in the cache. Some of them are not hitting in the cache. One thing that we realized, we have a cache that is fast, but we cannot really take advantage of how fast the cache is because warp A has to wait until I got all my data back. So let me ask you this question. With this memory divergence problem, anyone want to take a guess on what is the remaining benefit of having the cache? So to give you a hint, right? GPU demands a lot of bandwidth. Why? Because they have a lot of loads to the main memory. So you want your main memory to be able to handle a lot of loads that are happening at the same time. So if you have the cache, and let's say warp A supposed to send 8 data loads, but 3 of them is in the cache. It means that instead of sending 8 different data loads, you only send 5 data loads, right? So they have a lot less things inside DRAM. They filter out the potentially data loads that's supposed to go to DRAM. They are filtered out by the cache. So you've lessened the number of DRAM requests that are happening at each given time. It kind of reduces the burden on the main memory. So that's the benefit of the cache. They don't give, unless everything hit in the cache, they don't give the latency benefit. The requests are still not fast, but you don't have to send the request to the main memory. Our work basically asks this question, why can't we take advantage of the fast cache? Right? So the first observation is what we found here. It's called divergent heterogeneity. When you look at memory divergence, you have warps that look like this. If you have warps that look like this, both of them would stall for roughly the same amount of time, right? Because they all go to DRAM. So this is the stall time, which is kind of bad, right? Why is this bad? You feel bad because the mostly hit warp type is only one more cache hits than I can benefit from the cache. And for the mostly missed warp, I have one cache hit, and do I care? No. If I make this a cache mess, it's almost the same a number of DRAM requests arriving in DRAM, so it's not going to affect anything. Or at least we are hoping that it's not going to affect much. So our first design goal is, well, can we convert mostly hit into all hits and convert the mostly miss into all miss warp type, which would look like this. When we do conversion, the all hit warps would basically benefit from the low latency of the cache. Then the mostly missed warp, just send that to DRAM. That one request will not add a lot more items in the queue, so you ended up reduce the stall time. The next question that I have to ask, right, if I want to actually get some meaningful conversion is, I need to ask, hey, can I do this? So if you look at the application, right, across all the warps, what I see is if I define the hit ratio on the y-axis as number of cache hits over all the axes inside the warp, inside each of the warp, you see that they are pretty stable. So on the x-axis is the time. 1 million cycle across 1 million cycles, that's quite a bit of time where they stay in one category. And this happened on most of these warps, right? So if I check every 1,000 cycle or every 50,000 cycles, I'm gonna likely see the same behavior, right? So we use this to categorize each warps into 5 different categories. I'll hit, mostly hits, something in the middle, which I'm not gonna help, right? Because that's kind of like in the middle. Mostly miss, which I'm gonna make sure the miss in the cache so that they yield the cache space to the mostly hit warp. And then I'll miss, which we'll just leave it alone because they all go to DRAM anyway. The second question that we want to answer is, well, if you measure the request latency even at the cache, you then realize that the GPU cache somehow is quite slow compared to CPU cache, which take around 10 cycles, 10 or 11 cycles. The GPU cache can take hundreds of cycles at some point. It can be tens of cycles or even 100 cycles. The reason why we saw that is if you look at the L2 cache, they are being banked kind of similar to the DRAM. Each bank has its own buffer. What we see is the requests going to different cache bank are not equal. There can be banks like bank 1 that you can see here where most of the requests go into there. So if you measure the stall time of the L2 cache banks, almost half of them have to stall for 20 more cycles. So our second goal is, well, if the requests are not going to benefit from the cache anyway, just don't even queue up. Why are you making everyone else slow by queuing up and you know you're not going to need it because your data is not there, right? If you can detect that this is a mostly missed warp type, bypass the cache, go directly to DRAM. Everyone with me so far? Any questions so far? All right, so let's continue with the mechanism that we propose. Basically, it's called memory divergence correction or MEDIC. And the first elements that we have to do is, well, we need to identify warp types, right? And the way we do this is pretty simple. We run the application without any technique that we have say so far for a few thousand of cycles. We try to measure the cache hit ratio to actually categorize each warp into one of the type. I'll hit, mostly hit, I'll miss, mostly misses. Then based on the warp type, we will perform bypassing. Bypassing basically skip using the cache, go directly to the main memory. If you're mostly miss or all miss, just go use the main memory, get your data from there. So you bypass the mostly miss and all miss accesses. Then when you get the data back from DRAM, we modify the insertion policy so that we deprioritize the mostly miss or all miss warp type. We put them in the LRU position, so they're likely to be kicked out right away, unless they are frequently accessed. They still allow frequently accessed data to remain in the cache. Then, in the memory controller, we break the queue, we break the buffer into high priority and low priority, so that the mostly hit and all hit, if they cannot, right? Let's say it's a compulsory cache miss. First time you see the cache block, then you go to the high priority queue, go to DRAM, and hopefully get service right away. Otherwise, for the mostly miss and all miss category, just use the low priority because I don't care about how slow you are. You are already slow in the beginning. I want to make sure I prioritize warps that are fast. Here's the results compared to the baseline, which we do nothing in the red bar. On the y-axis, we show the speed up over the baseline. So you want to be as high as possible. On the x-axis, there's multiple applications that we evaluated, including the average. The yellow bar is the state-of-the-art cache insertion policy that are proposed for the CPU. The green bar is the policy designed for the GPU called pcal that perform cache bypassing. And compared to all the two, both of the techniques, MEDIC, which is our proposal, on average gets about 21.8%. And you can see that there are some cases where we lose performance over the state-of-the-art design, right? Some of those are from, sometimes they are mischaracterized, the warp type are mischaracterized, or sometimes you bypass too many things. If you ended up with so many all missed category, then you are going to actually lose performance because you bypass too many things. MEDIC, but still on average, is effective in identifying warp types and taking advantage of this divergent heterogeneity. This is the work that we presented, and as I said, we actually also lowered the energy. This is done when I was a PhD student at CMU. This is presented in PAC 2015, the same conference as the metadata work that I presented earlier during the virtual memory lecture. That was 2020. This is done in collaboration with AMD Research and also my friends at Penn State University. Any questions about this work before we move on to the on-chip GPU? All right, so if there's no question on this work, let me move on to the next set of work. So we are kind of like done with the textbook GPU. If you have a textbook GPU related question, feel free to ask me, because then I'm gonna start talking about some of the work I've done on the GPU side that improve or hopefully improve the performance of the GPU. So modern chips that you buy, including mobile phone, including embedded processor, these days they come with the integrated GPU. What are the integrated GPU? Basically, they put the GPU on the same die as the CPU. They share the same memory. These integrated GPU share the same DRAM, which means that if you look at how many DRAM requests the GPU is sending, it's going to heavily interfere the CPU application, lead to lower performance. So remember our animation from the memory scheduler from last week? What will happen if I add the GPU in? So let's look at this. This is what will happen, or this is what I saw when I was working on this topic, right? What happened is all the cores will send requests to the GPU like usual, right? But I mean not to the GPU, to DRAM like usual. But the big thing is when you have the GPU on the chip, the GPU sends so many requests relative to the other CPU core, and they occupy a significant portion of the request buffer, right? What is the result of that? When you occupy a lot of request buffer, it means that you run out of room. If Core 2 want to send in more requests, you can't. Right? You can't send the request. The request has to be wait until you can inject the request. What's the downside of this? It might be okay. I mean, if you don't think too much about the effects of this, because the oldest request will still be in the window, right? So you can still schedule the oldest request. But a lot of memory scheduling work would look at each of these applications, and they will kind of categorize the application, look at what should I do with the application. If you don't see this incoming request from Core 2, the scheduler might miscategorize the behavior that, hey, it might be some light application. It doesn't send a lot of requests to DRAM. So you might want to prioritize Core 1 or Core 3 instead, right? So that's the downside. And with that downside, it can lead to poor scheduling decision. In this work, we basically ask, okay, what are the key functions of the controller? Because we want to redesign, right, the controller to be able to handle these kind of traffic. So the first thing is you want to maximize row buffer hits, right? Maximize the bandwidth, make sure you can kind of like still get a lot of row buffer hits. Our proposal introduced this concept called batch. Like basically, we is not the first one to introduce the batching concept, but we utilize the batch formation. You group requests within the same application into different batches. They have to be from the same row, going to the same row buffer. Then across different applications, that's where contention happens. That's where unfairness happens. So we want to maximize system throughput and maximize fairness. So the second stage of our design, once we have the batch, we look at each of the batch. Instead of looking at every single individual request, we just look at each of the batch. To make the scaling logic simpler, we schedule batches from different applications, and then these whole ideas, it allows us to decouple the functional tasks of the memory controller and partition them across much simpler hardware structure. Here's the first stage example. You have 4 cores. You have requests coming from core 2 going to row B. And let's say the next request also go to row B. We'll batch them together. And let's say you have the incoming request to a different row. In this case, we will form a different batch. This simplified a lot of the logic. You don't really need complex hardware to do this, because if you have subsequent requests going to the different row, you just detect the row ID and like, oh, it's a different row, that's a different batch. So it would be marked with a different batch ID. Then if you have other requests from core 1, you then batch these together as well. And let's say some time window expires, you don't want to wait for the next request forever. So once the time window expires, you also mark that as a batch. They become ready to be scheduled. And this will be done on all the cores, including the GPU. So once this is done, what you see is the batch formation at the top. Almost the same example I have earlier, except for the fact that we now add the GPU into the picture. And one thing I saw about the GPU is they have really good row buffer hit rate. So they tend to dominate everyone else and form really big batch. Right? Form really big batch because the requests all go to the same row. The stage 2 of our design is the scheduler, which basically sends this batch into the DRAM banks, right? Based on each of these banks. There are 2 policies for the batch scheduler. The first policy is shortest of first. Shortest of first is defined as, I'm going to pick the smallest batch, send to the designated location. As just simple, right? It's also been proven that this would minimize the queuing time and basically improve performance. But this also means that you kind of like break the row buffer locality. So also the other problem here, if I use shortage of first all the time, is the GPU will never get to be scheduled because GPU form a much bigger batches. So the second policy is round robin. The way round robin works is you just rotate who gets to send the batch. And as new requests comes, we will form different batches while you're sending batches in the either shortage of first or round robin manner. And our design, because we have 2 schedulers, with the probability of P, we'll use shortage of first, and probability of 1 minus P, we can use round robin. And this probability also give a nice knob that the OS, the operating system, can tune. Why is that the case? If P is high, you're likely to use shortage of first that prioritize CPU applications. If P is low, you're likely to end up with round robin, which is going to give a lot of priority to the GPU. Why is this good? Well, if the OS is knowing you're playing games, you might want to tune P to some low value to make sure GPU gets priority. if you alternate tab from your games to another Windows, you might want to tune P to be high so that you actually now give more priority to the CPU. And here's the performance improvement that we achieve, right? On the y-axis here is system performance, higher is better. The red bar is the best previous scheduler on different GPU weight. The way we measure this is we measure the GPU weight. How important is GPU for performance? The left side is I don't care about the GPU. I only care about the CPU application. I want them to run fast. The right side is I only care about the GPU. I'm running games, maybe it's like a first-person shooting game, and I don't want to get shot by your friends. So I will need to make sure my GPU performs well. So the right side, I care so much about the GPU performance. This is a region where the technique called Atlas, proposed by Yoongu Kim and one of my group mates. This is the work done in my group, presented at HPCA 2010. This is actually one of the papers that gets selected to be one of the IEEE micro topics, which is a collection of the top architecture paper of that year. The Atlas paper give good multi-core CPU performance. Then TCM, which is also presented by Yoongu Kim again, this is at Micro 2010, also get picked to become one of the IEEE micro topics. TCM give good fairness. Then the last fraction, if our friend FRCFS, right, which is what we learned during DRAM lecture, these give really good DRAM throughput. What we saw is across every spectrum here, we beat the best previous scheduler. So at every single GPU weight, SMS stage memory scaling actually outperformed the best previous works in the world on that particular weight range on a GPU. And here's the title of the paper called Stage Memory Scheduling. And this is a very few works on, I think if it's not the first work on the CPU, GPU memory scheduling, it's the very first few works in the world. This is done in collaboration with AMD Research. Gabriel Lowe is actually he was my PhD committee member, and he's one of the renowned researcher inside AMD Research. And this is presented in ISCA 2012, a long time ago, and we actually patent the idea to US patent number 8775762. So if you're curious, you can check out the patent as well as the paper. Any question on this work before we move on to talk about how do we move the data between CPUs and GPU? All right, so assume there's no questions so far. What we have to do now that we have the GPU, if it's a discrete GPU, the GPU card that you buy and plug to the machine, right? Unlike the previous work where the CPU and GPU share the same memory, now they share a different DRAM. GPU is now a slave to the CPU. CPU is a host. It sends the data over to the GPU, sends the compute kernel to the GPU, and it tells when to start the compute kernel. The GPU acts like a device. It takes the CPU command and executes the code and does it, right? So let's talk about the host and the device memory. CPU has its own DRAM, DDR4. GPU these days, GDDR6. I need to update the slides to GDDR6. These give higher bandwidth than DDR4, but they are about the same speed. These DRAM are connected through the PCIe or a much faster and much higher bandwidth NVLink. So you buy high-end GPU like A100, they're going to be connected through NVLink. These are still quite a lot slower than the link between the last level cache and DRAM. So if you want to look at the host memory versus device memory, the requirements is this. If you want to run something on a GPU, data must be on the GPU. If you want to run something or continue the task on the CPU side, data has to be migrated back to the CPU. This shared data has an explicit memory management. You have to define when to copy the data and when to copy the data back. To get performance, you can minimize the number of transfer to get performance. And this is one of the things that a lot of people never realize until they realize, hey, the program I'm coding on the GPU is slow. What can I do? Minimizing the number of data transfer or transfer the data ahead of time can lead to quite a bit of performance gain. Here's a typical operation. You have the CPU and the GPU. The first step when you write the GPU program is you need to run Cuda malloc. This is similar to like a typical malloc operation, but it's allocate the GPU memory as I highlight on the red box over here. Then when the data is ready to be transferred, you transfer the data through a command called Cuda Mem Copy. This will copy the data from the CPU memory in these green boxes to whatever you allocated on the GPU. Then you launch the kernel. When the kernel finishes, you have the complete data, you send it back. So this RAID data which finished gets sent back to the CPU, right? So this is basically the typical operations on the GPU side and how you launch the kernel. Then NVIDIA and GPU manufacturer come up with an idea of, hey, let's make the two memory a single unit, right? This is called unified virtual memory. Basically, the idea is to create the illusion that the two memories are under the same address space, which means that you can use the same pointer from the CPU and the GPU. They're the same pointer. Everything else is managed by the hardware. Instead of Cuda malloc, you then use Cuda malloc manage. You then get a pointer that is allocated and the hardware manage where the data should be. It can be on the CPU. It can be on the GPU. So here's how the unified memory works. Basically, this links, it connects these two memory together. If you need the data, there will be automatic data movement through demand paging. Remember, demand paging from virtual memory lecture is where you want the data, but the page of data is not in your memory. In this case, if the GPU wants the data, it demand page the CPU's memory to basically migrate the data over. And here's the benefit. On paper, this is awesome. It makes GPU similar to program. You don't have to manually migrate the data. What are the problems? You somehow need an oracle information to predict when to transfer the data, right? Sometimes it's not good enough. Sometimes it's mispredict, and then the GPU kernel is slow. It also doesn't work. It doesn't work when you want to have multiple applications that want to share the GPU. This doesn't work even with the most recent GPU in A100, regardless of what NVIDIA tells you. It still is not able to support when you want to have multiple applications and have dynamic sharing. Dynamic sharing is important and it's hard. This applies to non-UVM situations as well. And this can lead to lower performance, right? So making UVM workflow is still an active research area. It's really active research area. Let me tell you this actually, because I work in this area and I know how it is to NVIDIA, AMD, the research team over there, the research team and in academia, and the architecture community in general. One of the big problem is called memory oversubscription. What is memory oversubscription? When you have unified virtual memory, you can do Cuda malloc manage, right? And let's say you have two applications running. Both applications think the GPU, let's say it has 10 gigabytes of memory. So the first application, they, oh, okay, we have 10 gigabytes. I'm going to allocate 8 gigabytes. The second application comes in, they, okay, I have 10 gigabytes, so I'm going to allocate 4 gigabytes. What's the total right now? 12. Is that greater than the GPU's memory? Yes. What will happen? Performance will tank. It's how bad it is. So if you have unified memory with the demand paging, this automatic data movement degrade GPU performance in many cases that we try to run. So this is our work presented a few years ago in ASPLOS. We crashed the entire system because we run two applications at the same time, and we just intentionally allocate memory in a way that when you combine all the applications together, it's greater than the GPU's memory, and it crashed. Big problem. And the way programmers solve this is hand-tuned. You can prefetch the request, basically make sure the request arrive in the GPU and kick something out ahead of time to make sure that by the time GPU needs the data is already there. A standard technique is you can duplicate read-only data so that things can be shared. The downside of this is done manually. You have to have a really good knowledge of what's the working set at that time when you're running. Then, if you want to use virtual machine or container and use a GPU, you can't peek into someone else's program, so you don't know how much memory the other virtual machine needs, right? Which means that even with hand-tuning technique, it will fail if you have multiple applications. So there's a demand for an application transfer mechanism to manage this. And our proposal is that, so if you look at three different applications, 3D convolution, you see that this is like streaming accesses. So the y-axis is the page number. The x-axis is time. So as you go in time, you see that you're going to basically access the next page, the next page, the next page. This is really predictable. We call this streaming access. The actual working set is relatively small. The only downside of when you have unified memory for these type of application is you're just waiting for the eviction. You want to evict the page. Once you make room for the next page, you can bring it in, but you can prefetch it in. So it's not really much of a performance overhead. You can have the same application, the same type, you're streaming data access, right? On the y-axis here, it's kind of having the same trend, but there's reuse. Once you're at the top, you use the bottom part again. So there's quite a lot of reuse. The working set is still small, but the problem is these, because they're reused, you're moving data back and forth between the CPU's memory and the GPU memories a lot of time. Then there's these type of application where I cannot predict what they're going. This is random access. It has a large working set and cause a lot of thrashing to other applications. We will categorize these three applications into three different categories. The first two are regular application with no data sharing. The second type is regular application, but we have data sharing across different kernels. The third type is irregular application. Things are accessed at random. I have no idea where they're going to access. And then our proposal use or employ multiple techniques in order to solve different goals. The first goal is to hide eviction lanes for the first type, because that's where the bottleneck is. Hide eviction latency and reducing the number of data migration for the second type, because that's where the bottleneck is for the second type. The third type, we want to reduce the working set size because it will hopefully reduce number of thrashing. This blue, the blue box here is designed to address what I write on the orange box. Different techniques here are needed to mitigate different sources of the overhead. We propose our framework called ETC, Eviction, Throttling, and Compression. That's where ETC stands for. First, we classify applications. Again, because we have three different types, we need to be able to classify them into each of the type. Once we detect the type, we apply three different techniques: proactive eviction, memory-aware throttling, and the capacity compression. Here's the framework. Because no single technique can work for all applications, the proactive memory-aware throttling and compression work for each one of these types of application: regular application with and without data sharing, and the irregular application. What are you getting for each of the techniques? If you do proactive eviction, you reduce the eviction latency. If you do throttling, you then reduce thrashing and reduce amount of the back and forth data sharing. When you do compression, you kind of minimize the working set. So we apply proactive eviction for the first type, and we combine proactive eviction with compression for the second type, because we don't want to like make data moving between the two memory. And for the irregular application, we can't do much beyond compression and throttling. Make sure they are not as parallel, because it's going to cause a lot of thrashing that's bad for performance. Make sure they are less parallelizable, and then compress the memory. Make sure that still fit inside the GPU memory, because as long as you fit inside the GPU memory, you're okay. Here's the performance plot on the y-axis for all the three application types on the x-axis. The orange bar here is a baseline for 75% of the working set that fit in the memory. So this is not a too bad case. I have 10 gigabytes of memory in total. All the application wants 12.5 gigabytes. So I only 2.5 gigabytes over, which is not good, but not too bad. Our proposal, ETC, is able to recover the performance compared to the ideal performance results at the one bar here, quite a lot compared to the baseline. If you make the memory a little bit more precious in this way, 50% of the workload only fit inside the memory, which means that if you have 10 gigabyte memory, your working set is actually 20 gigabyte, because 50% of them only fit inside the memory. Then you still recover, you perform better, but it's not as good, right? So what you see here is we improve the performance quite a lot. Like it's effective at identifying the types and correctly apply the policy to improve performance, but there's still a lot of room to work on this area. This is a work done in, we present that just a year ago in AskFlaws. That was in April 2019. I was working with Chen Li. He was right now he's a professor at National University of Defense Technology in China. Done in collaboration with myself, folks at University of Pittsburgh, VMware Research, University of Texas Austin, and I guess ETH Zurich, because my advisor moved from CMU to ETH Zurich. And this is kind of like when I moved here to KMU TNB as well. So it's kind of like a lot of affiliation on the paper. And we still are working in this direction with Chen Li, as well as Chris Rosbach, as well as another set of colleagues in Korea on how to actually make a better unified memory substrate, how to manage the data better, how to reduce data migration, how to actually be efficient in using the GPU's memory. Any questions about this work before I talk about this TPU, Tensor Processing Unit? All right, so now that there's no questions, it's pretty silent. Let's talk about the next set of things that I want to kind of like cover in this class, even though it's the material for the advanced architecture. The reason why I want to cover this is because the TPU or Tensor Processing Unit is being popularized. They're used by Google, they're used by NVIDIA. And here's the idea behind it. Back in '82, a long time ago, about 40 years ago, H.C. Kung come up with the idea in IEEE computer. That was back in the day where people still submitted journal, and that was back in the day where the conference is not the top like they are still the top tier publications. Back in the day, journal is still also another like top tier kind of outlet. These days, we all if you work in computer related field, forget about journal. You go to top conferences like ISCA, Micro, Asphalt, HPCA, PACT, those conferences. You work in computer vision, then you go to ICCV, ECCV. Those are the top conferences. Those are the top venue for all paper in the world. And if you have a question about journal versus conference, I have a lot to say about that because Thailand is way behind compared to other countries. And I think Europeans also are way behind. Like basically right now, everyone needs to catch up to the US. But that's where most of the works are published. That's where most of the companies are interested at, and they read these papers carefully. And they actually try to recruit people to their companies when they read these papers. So let's go back to the old days, 1982. There's a paper called Why Systolic Architecture. This is the plot that comes from the paper, right? So the paper said instead of this is basically a typical CPU, right? You have the processing element, which is the processing core. You request data from the main memory. The memory gives the data back. It takes 100 nanoseconds. What you can do for some operations are this. When you finish the instruction feed it to the next processing element. So basically your data come here. It get processed into a different color, move here. It get then processed again to a different color, move here. It get processed again without going back to the memory. It get processed again without going back to the main memory to the next processing element, get processed again to the next processing element before you finish the whole operations and send back the data, right? So over here, what's the benefit? Can someone tell me what's the key benefit here? If moving from processing element is instant and moving data from memory and processing element is 100 nanosecond, what's the benefit?
More faster.
It's faster because you don't have a lot of data transfer between the processing elements and the memory, right? A lot of the techniques in hardware, even now, are from these idea of like, hey, don't move the data back. If you're still computing and you can retain the data in the processing element, stay there. So one of the example of these is convolution. What is a convolution? Convolution is like having two functions act like a train facing each other and they collide. When they collide, you multiply them together and you add it afterward. Basically, these are multiplication and summation. Right? Multiplication and summation. And when you do multiply add, the result get forward to the next processing element because you are convoluting, when you're convolving two functions. Right? You have two functions and you want to form convolution. So you have to convolve all the elements in a function. You can use a multiply add and build a systolic architecture. Similar to what I show here, there was a figure from the same paper that shows the design of a convolution array where you can have the function x and w and y, where y out is basically yn plus weight multiplied by xn. And you can do convolution this way, and it's going to be fast because you don't go to the memory a lot of time. Once you have the data, you just keep forwarding this data into the input elements. Another example we use all the time is FFT. Right? This is also from the same paper. It's a 16-point FFT that allows you to do conversion from the time domain to a frequency domain in parallel. These dots are multiplication, the dots you see in the figure. These dots are multiplication. You multiply by the weight. The weight is e to the 2 pi k over n. So if you know how FFT works, then you know that this dot basically, if you look at the real number axis and the imaginary number axis, the e to the 2 pi k over n, basically you revolve this between the real and imaginary number multiplied by 1. The absolute value of the multiplication factor you apply is 1, but it goes around that axis. So you have something plus I, some number, a plus p of I, right? This is imaginary number. So this is how you can do it. So what is a TPU? The TPU is basically this similar design, but you apply that on matrix multiply and convolution. Any questions? It's that simple. You minimize the data transfer between the main memory and the processing elements, and you just do everything in the processing elements before you store the data back to the main memory. And the TPU also utilize the same concepts. All right. So actually, we're done with the class now. One thing I want to remind you is the paper reading and the presentation, because not all of you finish presentation. Anyone want to take a slot today now that we have like about 15 minutes of time? I thought it would take longer because actually we have 65 slides and somehow I covered that in 2 hours. So first of all, any questions? Because I feel like I'm going through this relatively fast. And actually one of the main reasons why I go through my own talk, like my own work really fast, is I practice this talk quite a lot of time. Like I spent months preparing the SMS talk, and I spent also like a month preparing the medic talk. So I've been through the scripts like so many times. This is what I recommend you all to do when you actually have to give a talk. You need to practice. But anyway, any questions?
What about the correlation between energy efficiency and performance?
Oh.
Because I think in one of the earlier parts, you said you can increase the performance and reduce the energy.
Yes. So let me actually add this to the last lecture of this class, because it's a bigger discussion that is not just about the GPU. But the thing about the GPU is it's energy efficient because of these reasons. So if I go to these slides, so let me share the screen again. Oh, actually, I need to show the slide before I share the screen. Where is that here? If you don't mind, let me share this. Okay. You see the screen where you have the GPU core and the execution units. So typically in the CPU, you have to fetch, decode, execute, memory, write back for each instruction, right? GPU is more energy efficient in this regard because when you fetch, it's only one fetch unit. Decode, it's only one decode unit. That saves so much energy. It's only one instruction is a 64. So that's actually one of the big reasons why GPU consume less energy per operation. But if you look at power, power is a different story. So if you look at GPU card or video card power, you'll notice that this consumes hundreds of watts. As opposed to the CPU, it's only tens of watts, right? The GPU consumes a lot more energy. Why is that the case? Because even though the per operation is energy efficient, the GPU has such a high throughput that everything combined, it will consume more power. Still, within the same function, if you think about power, right? Power oops, 10. Power is energy over time, right? That's the equation. So if you save energy, but you also make time faster, so E goes down, T goes down, P can go up because T goes down way more. So it's good for energy. It's energy efficient, but it can consume more power. This power is important for embedded devices. Why is it the case? You might have noticed your power adapter for your desktop laptop is bigger than the mobile phone, right? Mobile phone is powered by the battery. So the peak power that you can actually achieve is way lower. One of the things that a lot of application developers and the hardware developer has to do for, say, mobile phone is they need to look at, okay, how much power that I can maintain and sustain. If it's greater than this, your phone will reboot because you don't have power, right? So this is another important aspect. So you improve performance, you improve energy efficiency. If you consume too much power, one of the key techniques that you can do is lower the frequency. Everything becomes slower, but you save energy. You also lower power. So that's just the technique called dynamic voltage frequency DVFS. Basically, you dynamically tune voltage and frequency to save power, or you tune it to improve performance and burn more power. It's kind of like when you need to run a marathon. If you know it's a marathon, you save power by running slower. If it's only 1 meter left and you know you have enough energy left, you just burst through that last 100 meters so that you can go to the goal line as fast as possible. So I'm going to go through this concept in more detail on the last lecture, but this is kind of like the overall high-level thought process behind these techniques. One thing that you might have realized, how many of you heard about the Apple lawsuit about like Apple kind of like slowing down your phone to save the battery without telling you? And anyone heard about this lawsuit? At least these stories in news. So it's actually real, but what I can say is this applies to all the processor. It's a really common technique that is everywhere. But like for example, the Intel chip, they don't call it powering down. They start with a low frequency and they call it turbo boost. Turbo boost means they're gonna power up to make things faster. Right? So these are common techniques that's been applied for years now, actually. So does that answer your question, Lucas?
Yeah, and also the follow-up question you already answered with the kind of energy efficiency per operation. So of course the power goes up, but if we look at a single operation, so then yeah, if it's limited by the power, then that's
So let me tell you a little bit more breakdown about what are likely to consume power. So basically, when you move data around, the way it consumes power is if you change from that bit location, if you have to change from 0 to 1. If you look at wires, if you have to flip from 0 to 1 or 1 to 0, that consumes energy. If you change, basically, if you send 2 pieces of data and they are all 0, nothing changed. You don't consume energy because nothing changed, right? When you need to change from 0 to 1 to and 1 to 0, that's where you have to actually drive the electrons and it costs the energy. So if you have a data, that's actually some work that already been published that talks about this. When you have bit flips from 1 to 0 or 0 to 1, that's where you count as it consumes energy. One more thing, moving data from the cache to the processor, because you move data through wires from DRAM to the cache, moving data to wires again, this operation takes energy. There's also this thing called leakage energy. You move data through wires, electron leaks out by its own nature, right? So this thing can also consume energy because you need to drive more of the signal to make sure they arrive at the destination. And even when you're not driving anything, electron will just leak out anyway. It's like over time, when you're not running anything, you lose power. That's kind of like a terminal power level that you need to maintain for your computer to be on. So these are some of the things that cost energy. So if you go back to your program, every single line of code costs energy, but if you have to load and store, that are likely to cost more. If you want to do multiply, they are likely to cost more than an add. If you want to do a division, that is likely to cost more than a shift, right? If you shift right by some number, it's actually the same as divide by 2 to the n. So if you can shift instead of divide, that will save power. If you can shift instead of multiply, that's also save power. If you are accessing data in the cache, that saves power compared to accessing data in the main memory. So any activity that costs time and cause data to move around, typically those will take more energy. All right. Any other questions? Okay, so let me double check this. So if I remember correctly, Boss and Opa, you need to each present, right? You have one more presentation. So if you're not going to do it this week, make sure you have time to at least present on the last week of class. The last week before the final exam, to check the academic calendar, I believe is the week after next week. If I'm not correct, I'm not wrong, my bad. If I'm not wrong, I think it's the week after next week. So please double check and make sure you have at least a review done over that time so you can drive the discussion. I'm gonna basically make about half an hour free for both of you so that you can present, unless you want to present today, because that's it for the class. I mean, if there's no presentation, you can ask me more questions, or yeah, basically that's all the content I prepared for today, and I thought it would take 3 hours or more. Actually, I ended up breathing to my skin and kind of talk without stopping. All right, so if there's no more question, I'm gonna finish the recording for today, and